So, ammonia. We hear about it all the time, right? It's supposed to be this amazing key to zero carbon shipping, a super powerful clean fuel for the future. But there's always a catch. And with ammonia, it's a big one. To actually use this stuff on a ship, engineers have to solve a whole series of really tricky puzzles. And these puzzles, they're hidden in its most basic physical properties.
All right, so let's get into it. Let's break down what actually makes ammonia so tricky. This isn't a fuel you can just, pour into a tank and call it a day. Its behavior is dictated by some pretty fundamental laws of physics that you just can't ignore.
And you have to understand, these physical properties aren't just a list of numbers in a textbook. They are the rules of the game. And if you want to use ammonia safely and efficiently, you have to become a master of those rules. They dictate the design of every single piece of the puzzle, from the fuel tank all the way to the engine itself.
Okay, puzzle number 1, containment. A fuel's no good to you if you can't keep it where you want it. And for ammonia, that means keeping it liquid. But the thing is, ammonia is constantly trying to escape, to turn back into a gas. So here's how engineers are trying to fight back.
The first thing you absolutely have to get your head around is a concept called latent heat of vaporization. Now, in simple terms, think of it as just this huge amount of stubborn energy a liquid needs to soak up before it can become a gas. And here's the weird part. This happens without its temperature even changing. For an engineer, this number is basically everything. It tells them how beefy their cooling systems need to be, how big their condensers are, and even how thick the insulation on the tank has to be.
Now, take a look at this comparison, because this is where it gets really interesting. See ammonia there in the middle? It has a really high latent heat. It's way, way higher than a typical refrigerant like R134a. This means it can absorb a ton of heat before it vaporizes. And that's a huge deal for system design. You need some seriously robust equipment to handle that kind of energy transfer.
Next up is the critical point. And you can kind of think of this as a one-way street for a gas. If you push it past this specific temperature and pressure, it turns into this weird state called a supercritical fluid. It's not really a liquid, not really a gas. And once it's there, you can squeeze it as hard as you want. It is never turning back into a liquid.
Oh, man.
For engineers, this is a hard red line, an absolute boundary you can never, ever cross.
For ammonia, that point of no return is 132.3 degrees Celsius at a whopping 113 bar of pressure. And this matters because every single component in that fuel system, every pipe, every valve, every tank, has to be built to never even get close to these conditions. Because if it does, you don't just have a small problem. You've completely lost control of your fuel. So how did they keep it under control? Well, this is where saturated pressure becomes an engineer's best friend. Think of it like a magic number. For any temperature you pick, there's one exact pressure that keeps the ammonia in a perfect, happy balance between liquid and gas. So by controlling the pressure in the tank with incredible precision, engineers can keep the ammonia right where they want it to be. Okay, so we figured out how to keep it liquid. But what about the consequences of its other properties? This next puzzle is all about two things: density and safety. How much fuel can you actually pack into a ship? And maybe more importantly, what happens if this stuff leaks? Now here are two terms that sound super similar but mean completely different things: density and vapor density. Density, that's the easy one. It's just mass per volume. It tells you how much fuel by weight you can cram into a tank. Vapor density, though, that one's all about safety. It's a comparison to air, and it tells you a very simple, very important thing. If there's a leak, is the gas going to rise up and disappear, or is it going to sink to the floor and create a huge hazard?
And what this table really shows us is that density is not some fixed number. You see, under typical storage conditions, liquid ammonia has a density of about 696 kilograms per cubic meter. Now that's a lot less dense than traditional fuel oil. And the immediate consequence of that? Well, it means for the exact same size fuel tank, a ship is carrying way less fuel by weight. And that directly impacts how far that ship can travel.
Now let's talk safety. Ammonia's vapor density is less than 1, which means it's lighter than air, most of the time. So a small gas leak at room temperature, it's going to rise. But, and you really have to pay attention here, this is the crucial part. If you have a leak of liquid ammonia, which is at minus 33 degrees, the cold gas that boils off is actually denser than the air around it. It's going to sink. And that one little fact completely changes everything about where you put your gas detectors and how you design the ventilation for the entire engine room.
So far, we've talked about problems that, with clever engineering, you can manage. But now we've arrived at the biggest, most unavoidable headache of them all, the constant, relentless creation of boil-off gas. Look, no matter how good your insulation is, you can't build a perfect thermos. You just can't stop heat completely. Some of it is always going to leak into a cold ammonia tank. And this slow, steady creep of heat causes a tiny but constant amount of that liquid to evaporate, or as engineers call it, to boil off. This never ever stops. It's a 24/7 problem that has to be managed, day in, day out.
And why is this such a monumental deal? It all comes down to this number. When one drop of liquid ammonia turns into a gas, it expands to 950 times its original volume. 950. Now just try to imagine that happening constantly inside a totally sealed tank. The pressure buildup would be absolutely relentless. It would just keep climbing and climbing.
Now, with other fuels like liquefied natural gas, there's an easy solution. You just vent the extra pressure into the atmosphere. Simple. But for ammonia, this is the absolute showstopper. Because it is toxic, you are simply not allowed to release it, period. And this one rule creates the single biggest engineering puzzle of all. What on earth do you do with all that boil-off gas?
Okay, so let's pull all of this together. All these different properties, they aren't just random facts. They are the literal blueprint for how you engineer a safe and reliable ammonia fuel system.
So the engineering blueprint becomes crystal clear. First, you have to manage heat, designing your systems around that super high latent heat. Second, you have to control pressure, making sure you always operate a safe distance from that critical point. Third, you plan for safety, using what we know about vapor density to put detectors and vents in exactly the right place. And finally, the big one, you must contain and manage every last bit of that boil-off gas.
And really, that's the key takeaway here. Latent heat, critical point, vapor density, boil-off, these are not just terms you memorize for a test. They are the fundamental, non-negotiable rules for building the ships of the future. And getting them right, well, that's the difference between a revolutionary new fuel and a potential disaster at sea.
All of this leaves us with one final and pretty huge question. We've seen the puzzles that physics has laid out for us, so what's it going to be? What new technology, what brilliant breakthrough in engineering is finally going to crack the code and solve this puzzle for good, and unlock the true potential of ammonia? Well, the race to find out is definitely on.